Okay, here's sneaky approach number one. The sphere. Let us take a point charge. Now, for Gauss's law, what we're going to build to, I've got the electric flux defined as the integral of the electric field dotted with the differential area vector integrated over a surface. The sneaky bit, well, what I'm doing here for Gauss's law has to do with that integral over a closed surface. So, I'm going to look at three closed surfaces. Here's the first one, the sphere. Suppose I take a point charge, and I could take any sort of three-dimensional shape, make that three-dimensional shape around the charge I'm looking at, and Gauss's law would be successful. We go through that in great painful detail. Were we doing this chapter fully? Here, I'm just going to cheat and use three sneaky shortcuts just to demonstrate, oh look, Gauss's law does work. Now, at this point, the integral of that differential area vector at all points is normal to the surface or radially outward. So, if I look at the electric flux over the entire surface, or if I look at the integral over a closed surface, that's what that circle means, a closed, a circle in the integral for a length means a closed loop. When I'm integrating over area, it means a closed surface. That's the integral of E dot dA. Now in this case, because the electric field is radially outward and the differential area vector is radially outward, that means that these are going to be parallel at all points. So what I'll get is, I'll get this integral of E times dA is equal to something. Let's find that out. Now, the electric field at a given point here will be, well actually, let's see here. Notice that because I'm integrating over the area, okay, the electric field happens to be constant over the surface area. That's the benefit to sneakily choosing a sphere. The electric field is constant at a given radius r. So I just have the integral over the area, so I have the electric field, which is let's see. What I've used kq over r squared times the integral of the surface area of that sphere, which will be 4 pi r squared. Now, if I define this constant k in a different term, because now I've got 4 pi, I want to look at this in a slightly different way. So let me write k as being equal to 1 over 4 pi times a different constant. And this constant epsilon naught measures the permittivity of space. So it's actually telling me something about the medium. I need to know the medium that it's in for this to work. Our basic value, well actually epsilon is the permittivity. Epsilon naught is the permittivity of free space, which is 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. But if I write that in here, then I have this integral, E over dA is equal to 1 over 4 pi epsilon naught times r squared, divided by r squared, times 4 pi r squared, which will give me, let's see, 1 over 4 pi epsilon naught q over r squared times 4 pi r squared, or I'll get that integral is equal to q over epsilon naught. Now, that's the case for the sphere.